A cosmic heart beats in the dark. We are not talking about stars or planets, but something far more mysterious. Deep within the cores of distant galaxies, supermassive black holes are pulsing with a steady, rhythmic energy. Astronomers call these objects black hole breathers. They defy the classic image of a silent, all-consuming void, revealing instead a dynamic and almost living cadence in the most extreme places imaginable. By the end of this, you will understand how these cosmic heartbeats are reshaping our fundamental ideas about gravity and chaos. What could cause a billion solar mass monster to pulse like clockwork, and what happens when that terrifying heartbeat suddenly stops? What does it mean to find such familiar rhythm in the most alien depths of space? This rhythmic pulse is the defining signature of a black hole breather. To understand what that means, picture not the black hole's event horizon, the point of no return, but the furious storm of matter and energy swirling just outside it. A supermassive black hole, often weighing millions or even billions of times the mass of our Sun, sits at the heart of a galaxy like a gravitational anchor. Vast clouds of gas, dust, and even entire stars are pulled into its overwhelming grip. This material does not fall straight in, however. It spirals inward, forming a superheated, frenzied whirlpool called an accretion disk. Temperatures here soar to millions of degrees, causing the disk to glow fiercely across the electromagnetic spectrum, especially in powerful X-rays. Occasionally, the black hole also launches colossal beams of energized particles, known as relativistic jets, shooting out from its poles at nearly the speed of light. A black hole breather is a system where the brightness of this entire chaotic region, the disk and often the jets, does not shine with a constant glare. Instead, it brightens and dims with a startling regularity. It pulses. Astronomers detect these pulses as rhythmic bursts of energy, with the period, the time between one pulse and the next, following a steady clockwork that can range from a few minutes to several years. The black hole itself, the singularity, remains silent and dark. The heartbeat we observe is the sound of the storm around it, a cosmic lighthouse flashing with a precision that seems utterly at odds with the chaos we expect from such a violent environment. This transforms our classic image of a black hole from a passive, silent pit into something far more dynamic, an engine that doesn't just consume but rhythmically expels energy, almost as if it were breathing. That steady cosmic pulse was first heard not from a distant galaxy but from our own Milky Way. The year was 1994, and a satellite called the Rossi X-ray Timing Explorer was scanning the heavens, tuned to the high-energy language of X-rays. It locked onto a strange object known as J1034+396, a binary system where a stellar mass black hole, about a dozen times the mass of our Sun, was locked in a deadly dance with a companion star. The black hole was actively feeding, stripping material from its neighbor and creating a brilliant, hot accretion disk, but the data revealed something astonishing. The X-ray light from this system was not just flickering randomly. It was pulsing with a precise, metronomic beat, brightening and dimming in a cycle that repeated every 40 to 50 minutes. It was a perfect, regular rhythm emerging from the chaos of a stellar graveyard. The discovery sent shockwaves through the astrophysics community. Nothing like this had ever been seen before from a black hole. The phenomenon was so striking, so eerily familiar, that researchers did not hesitate to give it a profoundly human name, a heartbeat. This was the first undeniable evidence that black holes could exhibit such clockwork behavior. GRS-1915+105 was a microquasar, a small-scale version of the monstrous quasars found in galactic cores. Its discovery was a revelation, a proof of concept written in X-rays. It told astronomers that if a small black hole could pulse with such regularity, then perhaps the supermassive giants at the centers of galaxies could do the same, just on a vastly grander and slower scale. The first heartbeat had been found, and it opened our ears to a whole new symphony in the dark. That discovery of a stellar heartbeat was just the beginning, a whisper compared to the thunder that was to come. The real mystery lay in scaling this phenomenon up, from a black hole a dozen times our sun's mass to the true monsters of the cosmos. Could a supermassive black hole, an entity with the gravitational weight of millions or even billions of suns, also pulse with such eerie regularity? And if so, what kind of cosmic clock could possibly govern it? The answer came from a galaxy over 500 million light-years away. In 2007, astronomers trained the XMM Newton Space Telescope on a galaxy known as RE J1034+396. At its heart sat a supermassive black hole, actively feeding and shining as what we call an active galactic nucleus. When they analyzed the X-ray data, they found something that should have been impossible. The brilliant core was not shining with a steady light. It was pulsing, brightening and dimming with a clear, repeating rhythm. The period, the time between one pulse and the next, was about 1 hour. This was the first confirmed supermassive black hole heartbeat ever detected, and its implications were staggering. Here was a phenomenon first seen in a small system within our own galaxy, now echoing from a cosmic giant millions of times more massive and 500 million light-years distant. This proved the heartbeat was not some quirky feature of small black holes. It was a fundamental behavior that could scale across the universe. An hour-long pulse from such a colossal object is almost incomprehensible. Think of the sheer scale involved. The accretion disk around a supermassive black hole is not a neat, compact whirlpool. It is a vast, turbulent sea of gas and stars, often larger than our entire solar system. For the entire brilliant region to brighten and dim in unison on such a precise schedule suggests a level of coordination that defies simple intuition. It is as if every wave in a stormy ocean suddenly rose and fell together once every hour for centuries on end. The discovery of RE J1034+396 did more than just add another data point. It opened an entirely new field of study. It forced astrophysicists to ask entirely new questions. What universal physical process could create such a steady rhythm in environments that differ so wildly in size and power, from a stellar mass black hole to a supermassive one? And how could that rhythm persist for what are likely eons, seemingly undisturbed by the incredible chaos swirling all around it? The search for an answer would lead scientists to one of the most powerful and chaotic forces in the universe, gravity itself. The chaos surrounding a supermassive black hole is not random. It is a structured, albeit violent, engine, and to find a steady pulse within it, we must first understand the machinery. This engine is known as an active galactic nucleus. At its absolute center is the event horizon of the supermassive black hole, the silent point of no return. But everything that creates the brilliant light we see happens just outside this dark boundary. Imagine a vast, flat whirlpool of gas and dust stretching for billions of miles, spiraling inward at nearly the speed of light. This is the accretion disk. Friction within this disk heats the material to unimaginable temperatures, millions of degrees, causing it to glow with intense X-rays and ultraviolet light, outshining the entire surrounding galaxy. Perched above and below this seething disk is a mysterious region of superheated electrons called the corona. Think of it as the engine's fiery exhaust chamber, a cloud of magnetically charged plasma even hotter than the disk itself. And often, from the very poles of the black hole's rotation, erupt the most spectacular features of all, the relativistic jets. These are beams of charged particles, accelerated by unimaginable magnetic fields to almost the speed of light, shooting out perpendicular to the disk for thousands of light years. This entire frenzied complex, from the disk to the corona to the jets, is what astronomers observe as a brilliant quasar or active galaxy. Yet within this apparent bedlam, there exists a zone of surprising order. Just outside the event horizon lies a critical boundary known as the innermost stable circular orbit. This is the final parking spot where matter can still orbit the black hole safely. Any closer and it plunges irrevocably inward. This orbit acts like the edge of a cosmic drain, and its size is dictated solely by the black hole's mass and spin. It is a fixed point in the chaos, so when we speak of a black hole breather, when we detect that steady pulse of light, we are not hearing the black hole itself. We are listening to a rhythm emerging from this specific, structured engine, the accretion disk, the corona, and the jets. The pulse must be a symptom of something changing in a regular, repeating cycle within this high-energy region. But what could make such a violent, turbulent system beat with the precision of a clock? The answer lies not in the material, but in the very fabric of space and time being twisted around it. The steady rhythm of a black hole breather demands an equally precise physical explanation. How can the furious storm around a singularity settle into a cosmic metronome? The leading theories all point to one culprit, the extreme physics just outside the event horizon. The first and perhaps most intuitive model is known as pulsational instability, sometimes called the light bulb model. Picture the inner part of the accretion disk, that superheated whirlpool of gas. As it spirals inward, it is compressed and heated to incredible temperatures, producing an immense flood of radiation, mostly in X-rays. This radiation exerts an outward pressure. In the pulsational instability model, this creates a delicate, self-regulating cycle. When the inner disk gets too hot and bright, the intense radiation pressure actually pushes material outward, causing that region of the disk to puff up like a balloon. A puffed-up disk cools down, which makes it dimmer. With less radiation pressure holding it up, the material then falls back inward, where it is compressed and heated again, reigniting the brilliant glow. This cycle of expansion, cooling, collapse, and reheating could repeat with clockwork regularity, creating the observed pulses in X-ray brightness. It is a cosmic engine with a built-in thermostat, a heartbeat driven by the balance between gravity's inward pull and radiation's outward push. But what if the heartbeat is not the disk brightening and dimming, but a lighthouse beam sweeping past our view? This is the core of the jet precession theory. Many active black holes fire those colossal jets from their poles. According to this idea, the entire jet system, or perhaps the inner part of the accretion disk that anchors it, might be wobbling. This wobble, called precession, is like a spinning top slowly tracing a circle as it rotates. If a brilliant jet is wobbling in this way, it would periodically point more directly at Earth, then away, then back again. From our perspective, the jet would appear to brighten and fade in a steady rhythm. Even if the jet itself is shining with constant power, we are simply seeing it from a changing angle. This model elegantly explains why some heartbeats are seen only in specific types of light, like radio waves associated with jets, and not always in the X-rays from the disk itself. A third compelling idea delves into the magnetic furnace of the corona. The magnetic flux eruption model suggests the heartbeat is a build-up and release of magnetic energy, similar to a solar flare but on a galactic scale. The turbulent, magnetized plasma in the black hole's corona could act like a twisted rubber band. Magnetic fields are stretched and wound up by the disk's rotation, storing vast amounts of energy over time. When the tension becomes too great, the fields snap and reconnect in a catastrophic eruption. This explosion releases energy, heating the corona and creating a burst of high-energy light. The system then resets, the fields begin winding up again, and the cycle repeats. The regularity of the pulse would be set by how long it takes to build that critical magnetic tension. So how do astronomers test these competing ideas against the silent pulse of a distant galaxy? They become cosmic detectives analyzing the fingerprint of the light. They do not just measure the timing of the pulses, they dissect the entire spectrum of energy emitted with each beat. If the pulsational instability model is correct, the X-rays and optical light from the disk should pulse in sync, both dimming as the disk puffs up and cools. In the jet precession model, the radio waves from the jet might pulse strongly, while the X-rays from the disk remain steady. The magnetic eruption model might predict a specific pattern, a sharp spike of high-energy gamma rays coinciding with the main pulse. By observing the same black hole breather across the entire electromagnetic spectrum, from radio waves to gamma rays, scientists can compare its behavior to the predictions of each theoretical model. It is a painstaking process of matching a cosmic rhythm to the intricate steps of a physical dance, one that may ultimately reveal not just why these hearts beat, but what they are truly made of. The galaxy RE J1034+396 offered a perfect laboratory. When the European Space Agency's XMM Newton telescope first observed it in 2007, the data revealed a pattern so clean it seemed almost artificial. Its supermassive black hole, shining as a brilliant active nucleus, was emitting X-rays not in a chaotic flicker, but with a precise, repeating pulse. The period was almost exactly 1 hour. Think of the scale involved. The region producing this light, the innermost accretion disk and corona, is unimaginably violent, a place where space and time are warped beyond recognition. Yet from that chaos emerged a rhythm as steady as a ticking clock. What made this discovery so extraordinary was not just the detection of the pulse, but its astonishing stability. When astronomers pointed XMM Newton back at the galaxy years later, the heartbeat was still there, ticking away with the same 1 hour period. It had not sped up, slowed down, or faded into noise. This longevity is what truly defines a black hole breather and deepens the mystery. Most cosmic phenomena are transient, flashes in the pan on galactic timescales. A stellar explosion might last weeks, a tidal disruption event a few months. But RE J1034+396 has maintained its rhythm for the entire duration we have been watching, suggesting this is not a fleeting event, but a fundamental, persistent state of this black hole's engine. The clarity of the signal is equally compelling. In the messy data of astrophysics, clean periodic signals are rare treasures. This one stood out like a pure tone heard over the roar of a waterfall. That clarity allows scientists to test their models with unprecedented precision. Yet, it also presents a profound puzzle. How can such a long, stable period be generated so close to the black hole? The physics of the innermost stable orbit suggests that the orbital period of matter there is only a matter of minutes for a black hole of this size. A 1 hour heartbeat implies the rhythmic process must be happening farther out in the disk, in a region where matter orbits more slowly. But then, how does the entire luminous region coordinate its brightening and dimming so uniformly, a synchronization across millions of miles that lasts for years? It is as if every section of a vast, stormy ocean rose and fell in perfect unison, once every hour for centuries. The stability of this particular cosmic heart challenges our understanding of how accretion disks work, suggesting there is an underlying order to the chaos that we are only beginning to perceive. Its steady tick is a question written in X-rays, one that continues to draw the gaze of telescopes and the curiosity of scientists. A reminder that sometimes the deepest mysteries announce themselves not with a bang, but with a relentless, patient beat. The hunt was on. With one confirmed supermassive heartbeat echoing from the cosmos, astronomers immediately began searching the skies for others. This was no longer about a single anomaly. It was about understanding a potential new class of object, a population of black hole breathers. The search, however, is a monumental challenge of patience and precision. It requires catching the faint, rhythmic whisper of a distant engine over the constant roar of the universe, and it demands a new generation of cosmic detectives armed with specialized tools. Several other active galaxies have since emerged as strong candidates, each with its own tantalizing rhythm. Take the galaxy known as MS2254.9-3712. Observations hinted at a possible oscillation in its X-ray output with a period of roughly 2 hours. Then there is the famously strange object called 1H0707-495, an active galaxy whose light shows incredibly rapid and complex variations, with some analyses suggesting a hidden, repeating pattern buried within the noise. These candidate signals are called quasi-periodic oscillations, or QPOS. The quasi is the crucial, frustrating part. It means the rhythm is there, but it is not perfectly clean or stable like the heartbeat of RE J1034. It might drift in frequency, fade in and out, or be partially obscured by other fluctuations. Confirming these as true black hole breathers is incredibly difficult. The problem is twofold. First, you need long, uninterrupted stares at these distant galaxies. A telescope in low Earth orbit, like the brilliant XMM Newton, is blocked by our planet every 90 minutes, chopping the data into fragments. To catch a rhythm that might repeat only once every few hours, you need a single, unbroken observation that lasts for days, something only a handful of missions can provide. Second, the signals themselves are often incredibly faint, buried beneath the random flickering of the turbulent accretion disk. It is like trying to hear a specific, soft chime in a room full of clanging bells. This is where a new wave of technology enters the story. Enter NICER, the Neutron Star Interior Composition Explorer. Mounted on the International Space Station, NICER is an X-ray timing instrument with a unique advantage. Its location allows for those incredibly long, uninterrupted views of the cosmos, free from the periodic occultation by Earth. While originally designed to study the dense interiors of neutron stars, its exquisite sensitivity to the timing of X-ray pulses makes it a perfect instrument for listening to the hearts of black holes as well. It can gather the clean, continuous data needed to tease out those subtle, quasi-periodic signals and determine if they are truly the steady breath of a cosmic giant or just cosmic static. The search is a slow, meticulous process, a detective story written in data points collected over years. Each candidate is a clue, and each new, more powerful observatory planned for the future, like the European Space Agency's Athena mission, is a sharper magnifying glass. We are mapping the cadence of these mysterious hearts, one painstaking observation at a time, slowly learning whether the steady beat we first heard is a rare solo performance or part of a vast, rhythmic chorus spread across the universe. The key to this cosmic rhythm likely lies in the turbulent whirlpool of the accretion disk itself. Think of this disk not as a smooth, flowing river of gas, but as a churning, chaotic ocean. The material spiraling toward the black hole is not uniform. It comes in clumps and waves, creating regions of higher and lower density. This is where the concept of an instability becomes critical. An instability is simply a condition where a small disturbance, instead of smoothing out, gets amplified. In the extreme environment of an accretion disk, several types of these instabilities can arise. One of the most promising for creating a steady pulse is related to pressure. As gas in the inner disk is compressed and heated, it radiates tremendous energy. This radiation exerts an outward pressure. If the rate of heating and the resulting pressure build up in a specific, unbalanced way, it can cause the inner disk to rhythmically expand and contract. Picture a pot of water coming to a boil. Bubbles form at the bottom, grow, and rise to the surface in a somewhat regular pattern. In the accretion disk, pockets of overheated gas might behave similarly, puffing up, cooling, and then collapsing back down in a repeating cycle that modulates the entire region's brightness. This is not a perfect mechanical oscillation, but a self-regulating feedback loop born from chaos, a natural resonance of the disk's own violent physics. This leads us to a revolutionary idea, accretion disk seismology. Just as geologists learn about Earth's hidden interior layers by studying how seismic waves from earthquakes travel through the planet, astrophysicists can use the pulses from a black hole breather to probe the invisible structure of an accretion disk. Each pulse is like a sonar ping sent through the maelstrom. The properties of that ping, its frequency, its strength, and how it changes over time carry encoded information about the medium it traveled through. The steady period of the heartbeat is the most crucial clue. In a simplified model, the pulse period should correspond to the orbital period, or a multiple of it, at a specific radius within the disk. A 1-hour pulse, for instance, tells us that the phenomenon causing the rhythm is happening at a distance where matter takes about 1 hour to orbit the black hole. This immediately gives scientists a ruler. By combining the pulse period with the known mass of the black hole, which can be estimated by other means, they can calculate the approximate size of that inner resonant region. It is a direct measurement of the disk's geometry at its most violent point, a place no telescope can ever hope to image directly. Furthermore, the character of the pulse acts as a diagnostic tool. Is the pulse sharp and clear or broad and messy? This hints at the density and temperature of the gas in that region. Does the pulse appear in some wavelengths of light but not others? This reveals which part of the engine is oscillating, the hot inner disk, the overlying corona, or the base of a jet. By listening carefully to the heartbeat, astronomers are essentially performing a remote ultrasound on a cosmic monster. They can map the conditions just outside the event horizon, testing theories of gravity in its most extreme regime and understanding how energy is extracted from the black hole's spin. Every steady tick from the dark is a data point, transforming these mysterious breathers from celestial curiosities into precise laboratories for fundamental physics. The rhythm is no longer just a strange behavior, it is a language, and we are slowly learning to decipher what the darkness is trying to tell us. But to truly listen to a black hole's heartbeat, we must first understand the stage on which this rhythm plays. That stage is not a flat, neutral space. It is a dynamic, twisting fabric sculpted by the most extreme gravity in the universe. This is where Einstein's theory of general relativity becomes the essential script. Near a supermassive black hole, gravity does not just pull on objects, it warps the very geometry of space and time. This profound distortion does not merely exist in the background, it actively participates in the cosmic pulse, bending the beat we observe in ways that turn a simple signal into a complex test of fundamental physics. Consider the phenomenon of frame dragging. A spinning black hole does not sit still. Its immense rotation literally drags the fabric of space-time around with it, like a spinning ball submerged in thick honey. This creates a vortex effect, forcing any nearby matter in the accretion disk to be swept along in the direction of the spin. This relentless twisting can influence the rhythm of the disk's instabilities. It might help synchronize different parts of the turbulent flow, acting as a cosmic conductor that orchestrates the chaotic motions into a coherent, repeating pattern. The heartbeat period we measure could be a direct imprint of this space-time vortex, a rhythm set not just by orbital motion, but by the very rotation of the black hole itself. Then there is gravitational lensing, another bizarre effect of warped space. The black hole's gravity is so intense that it acts like a lens, bending the paths of light rays emanating from the far side of the accretion disk. Some light that would normally shoot off into empty space is curved around the black hole and directed toward us. This means when we look at the disk, we are not seeing a simple, flat structure. We are seeing a distorted mosaic where light from the back of the disk is bent over the top and bottom, making the entire region appear brighter and more complex. If a hotspot or a flare develops in the disk, its pulse of light would reach us not just directly, but also via these longer, lensed paths. This could smear the signal, making a sharp pulse appear broader, or even create faint echo-like repetitions of the main beat. The clean rhythm we detect is therefore filtered through this funhouse mirror of spacetime. The most tantalizing connection, however, lies in a specific orbit. General relativity predicts a critical boundary just outside a black hole called the innermost stable circular orbit. This is the final place where matter can still travel in a stable path before it is inevitably doomed to plunge inward. The orbital period at this specific radius is a fundamental frequency set by the black hole's mass and spin. Many astrophysicists suspect the heartbeat period we observe is not a random number. It could be, or be directly related to, this orbital period at the innermost stable orbit. If that is true, then every steady pulse from a black hole breather is more than just a curiosity. It becomes a direct measurement tool. By carefully timing the heartbeat, we can potentially weigh the black hole with incredible precision and even gauge how fast it is spinning. We are using the rhythm of light to probe the very architecture of warped spacetime, testing Einstein's century-old predictions in an arena he could only imagine. Each tick from the darkness is not just a beat, it is a question posed by gravity itself, and we are finally learning how to listen for the answer. The steady pulse of X-rays may be only half the story. For many of these cosmic giants, the most spectacular display is not the glow of the accretion disk, but the colossal beams they fire into intergalactic space. These are the relativistic jets, and evidence is mounting that their fury is intimately tied to the black hole's rhythmic heartbeat. In several active galaxies, astronomers have observed a tantalizing correlation. A burst of X-ray activity from the inner disk, a potential heartbeat pulse, is followed minutes or hours later by a flare of radio waves erupting from the base of a jet. It is as if a surge of power from the engine room travels down the exhaust pipe, creating a visible eruption. This synchronization points to a profound link known as disk-jet coupling. The hypothesis is direct and powerful. The same rhythmic process that causes the inner accretion disk to brighten and dim, perhaps a pulsational instability or a magnetic eruption, also governs the energy supply to the jets. When the inner disk puffs up or experiences a magnetic reconnection event, it does not just release light, it funnels energized plasma and strengthened magnetic fields along the black hole's rotation axis. This injects more power into the jet, causing it to flare brightly. The heartbeat, therefore, is not just a light show, it is the throttle controlling the most powerful engines in the universe. To understand how a steady pulse could make a jet appear to blink, consider the model of jet precession. Imagine a kinked garden hose with water blasting through at high pressure. If you hold the hose still, the water sprays in one constant direction. But if you slowly rotate the hose at the kink, the stream of water sweeps around in a circle, periodically dousing anything in its path. Now scale that idea up to cosmic proportions. The jet itself may be a constant, high-powered beam, but its launching point, possibly warped by the black hole's intense frame dragging or by interactions with the inner disk, could be wobbling. This wobble or precession would cause the jet to point toward Earth, then away, then back again. From our distant vantage point, the jet would brighten and fade in a steady rhythm, even though its power output is unchanging. We are simply seeing a lighthouse beam sweeping across our line of sight. Studying black hole breathers gives us an unprecedented window into the jet launching mechanism itself. These steady rhythms act like a controlled experiment, revealing the delay between a disturbance in the disk and the response in the jet. That delay tells us about the speed at which information and energy travel from the engine to the exhaust. By dissecting the heartbeat's fingerprint across X-rays, radio waves, and even gamma rays, we can map the chain of causality from the edge of the event horizon out to the jets that shape galaxies. The pulse is a diagnostic tool, letting us see how a black hole converts the chaotic rain of infalling matter into the focused, universe-spanning particle beams that define its most powerful state. But even the most steady cosmic rhythms can falter. The heartbeat of RE J1034+396, that textbook example of a supermassive black hole breather, did something profoundly strange after years of reliable pulsing. It grew faint, and then, for a time, it seemed to stop altogether. Observations in later years revealed its once clear X-ray pulse had diminished dramatically or vanished into the background noise. This was not an instrument error, it was a real change in the state of the black hole's engine. The silence was as telling as the beat. It meant these breathers are not permanent clockwork fixtures. They are dynamic, living systems that can enter and exit this rhythmic state, adding a deep new layer of mystery to their nature. Why would a cosmic heart skip a beat or fall silent for years on end? Several compelling theories attempt to explain the lull. The most straightforward involves the black hole's diet. The entire heartbeat mechanism depends on a very specific rate of material falling in from the accretion disk, not too much and not too little. Imagine trying to keep a campfire burning with a steady, rhythmic crackle. You need to add wood at just the right pace. If you suddenly dump a huge pile of logs on it, the fire will smother and smoke. If you let the fuel run too low, the flames will die down to embers. A black hole breather might operate on a similar principle. If a large, dense clump of matter, like a star or a giant gas cloud, was suddenly swallowed, it could overwhelm the delicate balance in the inner disk. The influx of new material could disrupt the self-regulating cycle of heating and cooling, drowning out the clean pulse in a burst of chaotic activity. Conversely, if the supply of gas from the wider galaxy simply dwindled, the accretion disk might become too faint and tenuous to support the instability that drives the rhythm. The heartbeat fades because the engine is starving. Another possibility points to a magnetic rearrangement. The magnetic fields threading the corona are thought to be crucial for both the heartbeat and for launching jets. These fields are dynamic, constantly being twisted and stretched by the disk's rotation. It is possible they can undergo a major reconfiguration, a sort of magnetic seizure. This event could permanently alter the structure of the corona, changing how energy is released. A steady, periodic release might shift to a more chaotic, burst-like pattern, effectively erasing the clean pulse we once observed. The black hole's heart hasn't stopped, but its rhythm has become arrhythmic, lost in a storm of magnetic noise. Perhaps the most fascinating idea is that the silence is part of a longer cycle. Some models suggest black hole breathers could oscillate between active, pulsing states and quiet, dormant ones over spans of decades or centuries. The heartbeat might return when conditions in the disk naturally reset themselves. This variability transforms these objects from simple curiosities into evolving characters in a galactic story. Their lulls teach us that the extreme environment around a black hole is not static. It is a seething, evolving ecosystem where balance is temporary and chaos is always waiting to reclaim order. The fact that we caught one in the act of changing state is a rare and valuable clue, a reminder that to understand the full nature of these cosmic hearts, we must listen not only to their beats, but also to their profound and telling silences. This fading rhythm leads us to a more violent and transient cousin of the black hole breather, a cosmic event that might represent the dramatic birth of such a pulse. When a star wanders too close to a supermassive black hole, the black hole's immense gravity overcomes the star's own self-gravity. The star is not swallowed whole. Instead, it is stretched and shredded in a process called a tidal disruption event. A long streamer of stellar gas is pulled apart, with roughly half of it flung away into space while the other half rains back down onto the black hole. This sudden, catastrophic influx of fresh fuel creates a brilliant flare of light that can outshine its host galaxy for months. Within that chaotic aftermath, astronomers are finding hints of order. As the stellar debris falls back, it forms a temporary, chaotic accretion disk, and in several of these events, the light from that newborn disk does not just fade smoothly. It flickers with a series of repeating flares, a quasi-periodic signal buried in the aftermath of destruction. these flickering TDES might be seen as temporary, one-time only black hole breathers. They offer a unique, time-limited laboratory to watch how an accretion disk forms and whether rhythmic oscillations can arise spontaneously from the chaos. It is a chance to witness the possible birth of a heartbeat. One of the most famous examples is an event called a J1034+396. After its initial brilliant flare, careful analysis of its X-ray data revealed a fascinating pattern. The fading light seemed to pulse with a potential period of about 131 days. While not as clean or stable as the heartbeat of RE J1034, this repeating signal suggested that as the stellar debris settled into a disk, some form of instability began to rhythmically modulate its emission. It was as if the violent death of a star had, for a brief cosmic moment, kick-started a metronome in the darkness. Studying these events is crucial because they let us observe the initial conditions. A supermassive black hole in a steady-state breather has likely been feeding at a stable rate for millennia. We are seeing a mature, balanced system. A tidal disruption event, by contrast, shows us the instant a massive amount of cold, dense stellar gas is violently dumped onto a black hole that may have been dormant. We get to watch the accretion disk assemble itself in real time and see if, under the right circumstances, it naturally begins to oscillate. The presence of these quasi-periodic flares in TDES supports the idea that the heartbeat mechanism is a fundamental physical process within turbulent accretion flows, one that can ignite under specific conditions. If the rate of infall and the properties of the debris are just right, a temporary rhythm can emerge from the stellar wreckage. This teaches us that for a sustained, long-term heartbeat like the one we observed for years, the black hole requires not just the right physics, but also a remarkably steady and consistent fuel supply. The flickering death throes of a star give us a glimpse into how these mysterious cosmic pulses might first begin to beat. The flickering aftermath of a tidal disruption event reveals a chaotic system trying to find its rhythm, but to truly map the steady heartbeats of established breathers, astronomers needed a more precise tool. They found it not in the pulse itself, but in the echo that follows. This technique is called X-ray reverberation mapping, and it works like cosmic sonar for the regions of warped space around a black hole. Here is how it works. The powerhouse of an active black hole is its corona, that cloud of superheated electrons hovering above the accretion disk. This corona emits intense, high-energy X-rays, often called hard X-rays. Some of these powerful photons blast directly out into space where our telescopes can see them, but a significant portion of them fire downward, illuminating the relatively cooler gas of the accretion disk itself. When these hard X-rays strike the disk, they are absorbed and then re-emitted at slightly lower energies as what we call soft X-rays. This process creates a distinct echo. Imagine standing in a vast, dark cave and shouting. You hear your direct voice first, and then, a moment later, you hear the echo bouncing back from the far wall. X-ray reverberation mapping operates on the same principle, but with light instead of sound. A flare or a change in the hard X-rays from the corona is the shout. The responding change in the soft X-rays from the disk is the echo. By meticulously measuring the time delay between the two signals, astronomers can literally map the geometry of this invisible realm. The delay tells them the light travel time from the corona down to the disk and then back up to our telescopes. If the delay is, say, 10 minutes, then simple geometry and the constant speed of light tell us the corona must be hovering about 5 light minutes above the disk. That is a direct physical measurement of structures near the event horizon. For black hole breathers, this technique has been revolutionary. In several of these rhythmically pulsing active galaxies, scientists have applied echo mapping to the heartbeat signal itself. They look for the hard X-ray pulse from the corona, and then they hunt for its softer echo reverberating from the disk. What they find is astonishingly consistent. The time delays are incredibly short, often just a few minutes to a few hours. This is the crucial evidence. Such brief echoes mean the corona and the inner accretion disk are extremely compact, packed into a region only a few times larger than the event horizon itself. It confirms that the entire heartbeat engine, the source of that metronomic pulse, is operating in the most extreme gravitational environment possible, right on the edge of the abyss. This compactness is exactly what the leading theories predict. A pulsational instability requires the inner disk to act as a coherent unit, something only possible if it is small and tightly bound. A magnetic eruption model needs the corona to be a concentrated furnace. The echo maps provide the blueprint, showing the tiny, violent arena where the rhythm is born. By listening to these faint cosmic echoes, we are no longer just guessing at the scale of these systems. We are measuring it directly, turning the heartbeat's reverberation into a precise ruler for the final frontier of space and time. This precision of scale only deepens the central theoretical puzzle. How can a supermassive black hole, whose feeding disk may span light days, produce a coherent pulse with a period of just 1 hour? This is the timescale problem, and it cuts to the heart of why black hole breathers are so perplexing. In a system that enormous, a signal should take days just to travel from one side of the disk to the other. For the entire luminous region to brighten and dim in unison on a much shorter schedule defies basic intuition. It is like expecting every person in a vast, crowded stadium to clap in perfect sync, without any visible conductor and with sound delays that should make coordination impossible. The leading explanation is that the heartbeat must originate in the very smallest, innermost region of the accretion flow, where orbital speeds are a significant fraction of the speed of light. Here, matter can complete an orbit in minutes or hours, matching the observed pulse periods. But this creates another puzzle. How does a localized oscillation in this tiny inner engine manage to modulate the light from the entire, vastly larger disk and corona that we see? The answer may lie in a process called reprocessing. A rhythmic change in the ultra-hot inner corona could flood the entire inner disk with a pulsing wave of high-energy radiation. This radiation, in turn, heats the disk's surface, causing its optical and ultraviolet light to pulse in time with the X-ray heartbeat from the core. The pulse is not a mechanical wave traveling through the gas. It is a flash of energy reprocessed across the entire environment, synchronizing the glow from a vast area almost instantaneously. Yet even this elegant idea faces a brutal challenge: turbulence. The inflow of matter into a black hole is not a smooth, orderly stream. It is a chaotic, clumpy, and magnetically turbulent mess. This constant churning should act like a powerful drag on any delicate rhythmic process, smearing out a clean pulse into random noise over a relatively short time. The fact that we observe heartbeats persisting for years suggests there is a remarkably robust physical mechanism that can resist this chaos. A self-regulating cycle so stable it can maintain its tempo against the cosmic din. This leads to a fierce debate among theorists. Is the heartbeat truly a global oscillation of the entire inner disk, a coordinated expansion and contraction like a breathing lung? Or is it caused by a localized hotspot, a single, brilliant flare orbiting the black hole like a lighthouse beam? A global oscillation better explains how the pulse appears so clearly across different wavelengths of light as the entire system's temperature changes. A hotspot model elegantly explains the short period, as it is simply the orbital period of a single dense clump. But a simple hotspot should be sheared apart by differential rotation in the disk within a few orbits, its signal quickly destroyed. To survive, a hotspot would need to be continually reignited, perhaps by a standing shock wave or a magnetic knot in the flow, which brings us right back to the need for a larger, global instability to create it. This is the theoretical impasse. The pulsational instability model, the jet precession model, and the magnetic flux eruption model each explain certain aspects of the data beautifully, but none perfectly solves all the puzzles. They struggle to simultaneously account for the precise period, the incredible longevity, the multi-wavelength signature, and the compact scale revealed by reverberation mapping. A unified theory of black hole breathers remains elusive because it requires us to perfectly model the most extreme, dynamic, and magnetically dominated environment in the universe, where general relativity and plasma physics collide in a turbulent soup. We are hearing the rhythm, but we are still deciphering the instrument. Every new heartbeat discovered and every old one that fades provides another crucial constraint, another piece of the puzzle that forces theorists back to their simulations. This is the thrilling, frustrating frontier of astrophysics, where a single, steady tick from the dark challenges our best models of how the cosmos operates at its most extreme. The precise rhythm of a heartbeat could be the key to unlocking one of a black hole's most elusive secrets, its spin. This rotation is not a trivial detail. A black hole's spin is a direct measure of its history, a record of all the matter and energy it has consumed, and it warps the fabric of space-time around it in profound ways. But how do you measure the spin of an object that emits no light of its own, whose very surface is darkness? The answer may be written in the steady pulse of a breather. General relativity gives us a critical clue. Just outside the event horizon lies that special boundary, the innermost stable circular orbit. The size of this orbit, and therefore the time it takes for matter to complete one loop around it, is not fixed. It depends entirely on two things: the black hole's mass and, crucially, its spin. A non-spinning black hole has a relatively large innermost orbit, but as a black hole rotates faster, the effect of frame dragging becomes so powerful that it pulls space-time itself into a vortex. This drag allows matter to orbit much closer to the event horizon without falling in. The closer the orbit, the faster the orbital period. For a maximally spinning black hole, matter can whip around at the very edge of the photon sphere, completing orbits in mere minutes or even seconds. This creates a direct, predictable link. The orbital frequency at the innermost stable orbit is a fundamental note, a base frequency set by the black hole's mass and spin. If the heartbeat period we observe from a black hole breather is indeed tied to this orbital period, or a harmonic of it, then that steady tick becomes a cosmic speedometer. By carefully measuring the pulse period and independently estimating the black hole's mass through other methods, astronomers could, in theory, solve the equation and calculate the spin. It is an elegant idea, using a natural oscillator in the accretion disk as a probe for the black hole's hidden rotation. The potential payoff is immense. Currently, measuring black hole spin is incredibly difficult and relies on complex interpretations of the X-ray spectrum from the inner disk. A method based on a clear, timed pulse could offer a more direct and potentially more precise measurement. It could allow us to survey the spins of supermassive black holes across cosmic time, asking fundamental questions. Do most of these giants spin rapidly, a sign of chaotic, prolonged feeding? Or do they have slower spins, perhaps from mergers that delivered matter from random directions? The heartbeat could tell us. However, this elegant picture is clouded by reality. The primary challenge is that the heartbeat period we measure is not a pure signal from a single orbiting particle. It is the product of a complex, turbulent system where magnetic fields, radiation pressure, and disk instabilities all play a role. These factors can influence the observed period, potentially masking the clean signature of the innermost orbit. The pulse might be generated slightly farther out in the disk, where orbital periods are longer, or it could be the result of a beating frequency between two different oscillations. Disentangling the pure gravitational signal from the plasma physics noise is the monumental task at hand. Yet, this is where the stability of the best breathers offers hope. A signal that persists unchanged for years suggests it is anchored to something fundamental, something as stable as the geometry of space-time itself. By combining heartbeat timing with other techniques like X-ray reverberation mapping, which measures the compactness of the corona, scientists can build a multifaceted model to constrain the spin. Each black hole breather becomes a unique laboratory. Its steady pulse is not just a curiosity, it is a precise tool being sharpened by observation and theory. If we can learn to read it correctly, that rhythm from the dark will tell us not only that a cosmic heart beats, but how fast the entire monster is turning. The promise of decoding these cosmic heartbeats lies not just in theory, but in a new generation of eyes on the sky. Our current telescopes have given us a glimpse, catching the loudest, steadiest pulses. But to truly understand the phenomenon, we need to hear the whispers, the faint, rapid beats, and the full chorus of breathers across the universe. That future is being built right now. The European Space Agency's Athena mission, scheduled for launch in the mid-2030s, is a game-changer. Designed as the most powerful X-ray observatory ever conceived, Athena will combine a huge collecting area with exquisite spectral resolution. This means it won't just detect a pulse, it will dissect it. Athena could observe the heartbeat of a distant black hole breather and simultaneously measure the reverberation echoes from its disk and corona with unprecedented clarity, mapping the geometry of the heartbeat engine in a single, detailed observation. It will have the sensitivity to find much fainter pulses from more distant or quieter black holes, potentially revealing that these rhythmic giants are far more common than we ever suspected. Alongside Athena, NASA is studying an equally ambitious concept called LINX. This next-generation X-ray telescope would push time, resolution, and sensitivity even further. LINX could catch ultra-fast oscillations, pulses that repeat in mere seconds or minutes from stellar mass black holes, giving us a slow-motion view of processes that happen in a blur with current instruments. It could monitor dozens of candidate breathers for months at a time, watching for the moment a heartbeat begins, fades, or changes tempo. This long-term, high-fidelity monitoring is the key to understanding the life cycle of these pulses. Do all supermassive black holes go through a breather phase at some point in their multi-billion-year lives, or is it a rare state requiring perfect conditions? Missions like Athena and LINX could provide the census data to answer that, but the heartbeat is a multi-wavelength symphony, and we need to listen to every instrument. This is where the square-kilometer array enters the story. The SKA, once built, will be the world's largest and most sensitive radio telescope network. Its revolutionary capability will be to monitor the sky with both vast scale and fine detail. For black hole breathers, the SKA could continuously watch the radio emission from their powerful jets. Imagine correlating a precise X-ray pulse from Athena with a subsequent flare in the jet observed by the SKA, nailing down the exact delay and energy transfer from disk to jet. The SKA could survey thousands of active galaxies simultaneously, searching for the telltale rhythmic flicker in their radio cores that signals jet precession. By combining the X-ray view of the inner engine with the radio view of its colossal outflows, we will finally see the full picture of how a black hole's heartbeat powers its most dramatic features. The ultimate goal is a cosmic census. Within a few decades, we could move from studying a handful of mysterious heartbeats to understanding their population statistics. How does the pulse period relate to black hole mass across the universe? Do breathers prefer certain types of galaxies? Do their rhythms change over cosmic time from the early universe to the present day? These questions transform the phenomenon from a fascinating curiosity into a powerful diagnostic tool for galaxy evolution itself. The steady tick of a black hole breather may become a standard ruler, a natural metronome we can use to probe the growth and influence of supermassive black holes throughout the history of the cosmos. We are on the verge of listening to the universe's rhythm section, and what we hear will redefine our place in the symphony. These cosmic heartbeats are born in a realm we can never visit, a place where our physical probes would be torn apart in an instant. So how do we test our theories about the forces that create them? We bring the universe into the laboratory. Scientists are now using some of the most powerful tools on Earth to build miniature, controlled versions of these chaotic systems, a field known as analog gravity. The goal is not to recreate the immense gravity of a black hole, which is impossible, but to simulate the behavior of the magnetized plasma that swirls around it. Inside the accretion disk, superheated gas is ionized, meaning its atoms are stripped of their electrons, creating a sea of charged particles. This plasma is not a calm fluid. It is a turbulent, magnetically dominated substance whose motions are governed by the laws of magnetohydrodynamics. These are the same fundamental laws that describe how plasma behaves in a fusion reactor or in the heart of a star. By recreating similar conditions of extreme temperature, density, and magnetic turbulence here on Earth, researchers can watch how instabilities form and evolve in real time. One of the most promising methods uses high-power lasers. Scientists fire immensely powerful laser pulses at a tiny, solid target, often a hair-thin piece of metal or plastic. The impact vaporizes the target in a fraction of a second, creating a miniature fireball of dense, hot plasma that expands rapidly. Within that explosive cloud, conditions arise that are startlingly similar to those in an accretion disk, with shock waves, turbulence, and magnetic fields being generated and tangled. By carefully designing the experiment, physicists can induce a specific instability and watch it oscillate. They can measure how long a perturbation lasts, whether it settles into a rhythm, and how magnetic fields either dampen or amplify the pulse. It is like building a tiny star in a jar to study the heartbeat of a galaxy. Another approach uses sophisticated plasma chambers, large metal vessels where magnetic fields confine and stir hot plasma for sustained periods. In these devices, researchers can directly test models of the pulsational instability thought to drive black hole breathers. They can inject a precise amount of energy into the plasma and observe if the system responds by settling into a regular pattern of heating and cooling, of expansion and contraction, mirroring the proposed cycle in an accretion disk. These laboratory pulses happen over microseconds, not hours, but the scaled physics can be directly analogous. The value of these experiments is profound. In space, we get only one snapshot, one set of conditions from each black hole. We see the heartbeat, but we cannot tweak the parameters to see what makes it speed up or fade. In the lab, scientists have complete control. They can adjust the plasma density, the strength of the magnetic field, the rate of energy input. They can run the experiment thousands of times, each time changing one variable to see its effect on the resulting rhythms. This allows them to validate the complex computer simulations that model black hole environments, providing a crucial reality check. When a simulation predicts that a certain magnetic field configuration will produce a steady pulse, that prediction can now be tested against a real, albeit small-scale, plasma in a laboratory on Earth. It turns abstract equations into observable phenomena. These terrestrial echoes of cosmic violence offer a unique bridge. They allow us to probe the universal plasma physics that we believe operates from the sun's corona to the edge of a black hole's event horizon. Every steady oscillation recorded in a plasma chamber brings us one step closer to understanding what makes a billion solar mass monster breathe with the regularity of a clock. The laboratory becomes a decoder ring, helping us translate the rhythmic signals from the dark into the fundamental language of physics. There is a profound and deeply human reason these cosmic rhythms captivate us. A heartbeat in the void feels strangely familiar, a whisper of order in a place defined by chaos. We are creatures wired to seek patterns, to find rhythm in the world around us, from the steady pulse in our own chests to the reliable turn of the seasons. We have always looked to the heavens and seen cycles, from the phases of the moon to the regular flash of pulsars, the spinning neutron stars we once nicknamed LGM for little green men because their signal was so unnervingly perfect. Finding a similar cadence in a supermassive black hole touches something primal. It suggests that even in the most alien and destructive environments, the universe operates with a kind of physics that can produce phenomena we intuitively recognize. This connection is not just poetic, it is a guiding light for science. The drive to understand black hole breathers forces us to blend disciplines that rarely speak the same language. To decode their pulse, we must marry the cosmic scale gravity of Einstein with the microscopic chaos of magnetized plasma physics. We need general relativity to describe the warped stage and magnetohydrodynamics to explain the turbulent actors upon it. It is a grand unification in miniature, happening in the most extreme laboratory nature provides. Every steady tick from a distant galaxy is a challenge, a puzzle that demands we push our theories to the breaking point and then beyond. But the importance runs deeper than fundamental physics. Understanding these rhythmic giants is a crucial step toward a complete picture of galactic life and death. A supermassive black hole is not a passive monster at the center of a galaxy. It is an active engine. Its feeding habits, its outbursts, and yes, its steady breaths inject energy and turbulence into the surrounding galaxy. This feedback can halt star formation by heating up galactic gas, or it can trigger new stellar births by compressing cosmic clouds. The heartbeat, therefore, is more than a curiosity. It is a signature of how the black hole is interacting with its home, a measure of its influence on a galactic scale. By learning to read this rhythm, we learn how these dark hearts regulate the growth and evolution of the galaxies they anchor, including our own Milky Way. In listening to their steady beat, we are not just solving a cosmic mystery, we are tracing the invisible threads that connect the fate of a black hole to the destiny of billions of stars. This cosmic rhythm echoes another we have long known, the steady flash of a pulsar. Pulsars are the collapsed cores of massive stars that died in supernova explosions. These neutron stars are only about the size of a city, yet they pack more mass than our sun into that tiny sphere. They spin at dizzying speeds, some completing hundreds of rotations every single second. As they spin, their intense magnetic fields funnel radiation into narrow beams that shoot out from their magnetic poles. If one of those beams sweeps across Earth, we detect it as a rapid, incredibly regular pulse of radio waves, a cosmic lighthouse blinking with a precision that rivals our best atomic clocks. For decades, pulsars were the champions of cosmic timekeeping. Their metronomic ticks a testament to the stability of spinning, magnetized spheres in the vacuum of space. Black hole breathers are an entirely different kind of clockwork. Their pulse does not come from the spin of a solid object. There is no surface, no magnetic pole to sweep a beam across our view. Instead, the rhythm emerges from the chaotic storm of matter and energy around the black hole, from the physics of the accretion disk and its corona. It is the pulse of a dynamic, fluid system, not a rigidly rotating one. This difference is written in their timescales. A pulsar's heartbeat is frantic, measured in milliseconds or seconds. A black hole breather's pulse is stately and slow, with periods ranging from minutes to years, reflecting the orbital timescales in a vast, swirling disk of gas. Their stability also tells a different story. A pulsar's spin is incredibly stable over human timescales, slowing down only gradually over millennia as it radiates energy away. A black hole breather's rhythm, while it can persist for years, is far more fragile. It depends on a delicate balance in the accretion flow, a balance that can be disrupted by a change in the black hole's diet or a magnetic rearrangement, causing the heartbeat to fade or vanish. The pulsar is a rigid, spinning top in empty space. The breather is a self-regulating engine in the midst of a continuous, violent storm. Finally, their energy sources are worlds apart. A pulsar shines by converting its own rapid spin and immense magnetic energy into radiation. It is a closed system slowly winding down. A black hole breather is powered from the outside by the gravitational energy of matter falling in from its accretion disk. It is an open system, a converter of infalling fuel into rhythmic light and powerful jets. One is a spinning magnet, the other is a breathing engine. Recognizing this distinction is crucial. It places black hole breathers not as faster or slower versions of pulsars, but as members of a new family of periodic objects, one defined not by rotation, but by the complex rhythmic dance between gravity, magnetism, and turbulent plasma. This understanding reframes the entire mystery, shifting our search from looking for cosmic spinners to listening for the resonant hum of cosmic engines. Finding the next cosmic heartbeat means understanding its perfect home. Not every supermassive black hole breathes with a steady rhythm because the conditions have to be just right. This is the Goldilocks zone for breathers, a delicate cosmic balance where the engine runs neither too hot nor too cold, but in a precise state that allows a pulse to emerge and persist. The most critical factor is likely the accretion rate, the speed at which the black hole is being fed. Picture a campfire again. To get a steady, crackling flame, you need to add wood at a consistent, moderate pace. If you dump an entire tree onto the fire all at once, you get a chaotic, smoky inferno. If you only add a few twigs, the fire dwindles to faint embers. A black hole breather might require a similar perfect feeding schedule. If the accretion rate is too high, the inner disk becomes overwhelmed. The inflow of gas is so dense and furious that any incipient rhythm is drowned in turbulence before it can establish itself. The system is in a chaotic, quasar-like state, brilliant but arrhythmic. Conversely, if the accretion rate is too low, there simply isn't enough fuel to power the powerful instabilities needed for a strong, observable pulse. The disk might be too faint and tenuous to support the self-regulating cycle of heating and cooling. The sweet spot is somewhere in the middle, a steady, sustainable trickle of material that keeps the inner engine hot and active, but calm enough for order to arise from the chaos. The magnetic field is the other crucial ingredient in this recipe. It is not just about having a magnetic field, but having one of the right strength and the right configuration. The field lines threading the corona act like the tendons of the heartbeat, transferring energy and potentially creating the periodic eruptions. If the magnetic field is too weak, it cannot organize the plasma or build up the tension needed for a rhythmic release. The disk's behavior would be dominated by fluid turbulence alone, which is messy and random. If the magnetic field is too strong and chaotic, it might drive constant, violent flares that also prevent a clean oscillation. The ideal might be a strong, ordered magnetic field that is anchored in the inner disk, one that can be steadily wound up by the rotation and then snap back in a predictable, repeating pattern. This magnetic geometry could act as a piston in the engine, driving the regular pulses we observe. So the Goldilocks zone is a dual condition, a perfect marriage of a moderate accretion flow and a well-ordered magnetic furnace. This leads us to wonder about the galactic neighborhoods that might foster such perfection. Does a particular type of galaxy host more breathers? The calm, settled environment of an elliptical galaxy, where gas supplies are often low, might starve the black hole, putting it below the necessary accretion rate. The gas-rich star-forming spirals, like our own Milky Way, might occasionally feed their central black holes in fits and starts, often triggering chaotic outbursts rather than steady rhythms. Perhaps the ideal cradle is a galaxy in a specific transitional phase. Consider a galaxy that has recently undergone a minor merger, absorbing a smaller companion. Such an event can funnel a fresh, sustained stream of gas toward the central black hole without the violent disruption of a major collision. This could provide that perfect, moderate fuel supply for millions of years, long enough for a heartbeat to establish itself. Alternatively, breathers might be found in galaxies where the black hole has just finished a major feast, like a tidal disruption event, and is now settling into a quieter but still active phase of digestion. The rhythm emerges as the chaos of the stellar debris settles into a more stable, persistent disk. If this speculation holds, it gives astronomers a treasure map. To find more of these rare objects, we should not just look at the brightest, most violent quasars or the silent, dormant giants. We should focus our search on active galactic nuclei with moderate luminosities, those in galaxies showing signs of recent, but not catastrophic, interaction. We should look for systems where X-ray observations show the clear, compact coronae revealed by reverberation mapping, a sign of a well-ordered inner engine. The next generation of telescopes will turn this speculation into a systematic hunt, scanning the skies for the specific signatures of this cosmic balance. Each new breather found will refine our map of the Goldilocks zone, telling us not just where these hearts beat, but why they choose to beat there, and perhaps for how long their fragile rhythm can last before the universe's chaos reclaims its own. The steady rhythm of a black hole breather may be more than a cosmic curiosity. It could be a faint signal from the very edge of our understanding of reality, a place where the known laws of physics break down. This brings us to the most profound and speculative implication of all. The extreme environment right outside the event horizon is the ultimate testing ground, the one place in the universe where the two great pillars of modern physics, Einstein's theory of general relativity and quantum mechanics, are forced to collide. General relativity describes gravity as the curvature of spacetime on immense scales, and it works flawlessly for predicting the orbits of planets and the warping of light around black holes. Quantum mechanics describes the bizarre, probabilistic behavior of matter and energy on the smallest scales, inside atoms and particles. For nearly a century, these two theories have been fundamentally incompatible. Unifying them into a single framework, a theory of quantum gravity, is perhaps the greatest unsolved problem in all of physics, and the mysterious pulses from a black hole breather might, just might, offer a tiny window into that unification. Why here? Because at the very boundary of a black hole, the event horizon, conditions become unimaginably extreme. Spacetime is curved beyond recognition by general relativity's rules, yet the scale is also unimaginably tiny. The quantum fuzziness that governs the subatomic world should, in principle, become important here too. It is a realm where the smooth fabric of spacetime predicted by Einstein might itself break down into a frothing sea of quantum fluctuations. Some theoretical models venture a breathtaking idea. The quasi-periodic oscillations we observe, those clean pulses from black hole breathers, might not be solely the product of plasma physics in the accretion disk. They could carry an imprint of quantum structures at the event horizon itself. One speculative proposal suggests that the event horizon is not a perfectly smooth mathematical surface. Instead, it might be composed of discrete quantized units of area, a pixelated boundary dictated by quantum gravity, much like how a digital screen is made of individual pixels. If this is true, the horizon could vibrate or resonate at specific frequencies. Another line of thinking proposes that information swallowed by the black hole is not lost forever but somehow preserved on its surface, leading to complex quantum interactions that could, in theory, produce periodic effects in the surrounding radiation. Now, it is crucial to state this is highly speculative. The dominant and well-tested explanations for the heartbeat still lie in the magnetohydrodynamics of the accretion flow, the classical physics of hot plasma and magnetic fields we have been discussing. The quantum gravity signal, if it exists at all, would be an incredibly subtle whisper buried deep within the much louder roar of the classical astrophysical processes. Isolating it would be like trying to hear a single, specific instrument in a symphony performed during a hurricane, yet the mere possibility is electrifying. It transforms black hole breathers from fascinating astrophysical objects into potential laboratories for fundamental physics. They become natural experiments set up by the universe itself, probing regimes of energy and curvature we could never hope to recreate on Earth. By meticulously observing the precise details of their pulses, the exact frequencies, how they decay or change over time, scientists could one day find a discrepancy, a tiny anomaly that no classical model of accretion disks can explain. That anomaly could be the fingerprint of quantum gravity. This connection elevates the entire pursuit. Studying these rhythmic giants is no longer just about understanding how black holes feed or power jets. It becomes part of the centuries-long human quest to understand the deepest rules governing reality. Each steady tick from the dark is a data point that could, in the distant future, help bridge the chasm between the cosmos of the very large and the realm of the very small. The heartbeat may be a message in a language we are only beginning to learn, a rhythm that holds the key to how space, time, and matter truly intertwine at the edge of existence. The data arrives as silent numbers on a screen, a graph of brightness over time, a visual heartbeat. But what if we could truly listen to it? Scientists have found a way to translate the light of these cosmic pulses into something we can experience directly: sound. This process is called sonification, and it transforms the abstract into the eerily tangible. Agencies like NASA take the precise X-ray light curves from observatories, the very data that reveals the steady pulse of a black hole breather, and map it onto an audible frequency. The brightness of the X-rays might control the volume while the passage of time dictates the tempo. What emerges is not random noise, but a tone, a rhythm, a melody born from a gravitational monster. You are not hearing sound waves that traveled through space, of course. Space is a vacuum, silent. Instead, you are hearing the data itself given a voice. The result is haunting. The steady, metronomic pulse of a breather like RE J1034+396 becomes a deep, resonant thump like a distant cosmic drum. A quicker, more chaotic flicker from a tidal disruption event might sound like a shimmering cascade of notes, a brief, violent symphony of stellar death. This auditory translation does more than just create a compelling piece of science outreach, though that is powerful in itself. It offers researchers a different way to perceive patterns in complex data. Our ears are remarkably good at picking out rhythms, repetitions, and subtle changes in tone that our eyes might miss in a crowded graph. A scientist might listen to a sonified data set and detect a faint secondary pulse, a slight waver in the rhythm, or an echo that wasn't immediately obvious visually. It becomes another tool in the detective's kit, allowing us to engage a different sense in the search for cosmic order. There is a profound beauty in this act of translation. It bridges the vast, impersonal scale of astrophysics with our own human experience. We have a deep, innate connection to rhythm and sound. To hear the steady beat of a black hole is to feel, in a visceral way, the reality of that distant engine. It transforms the phenomenon from a plotted line on a chart into something that feels almost alive, a rhythmic breath in the dark that we can now, in a very real sense, listen to. That sound makes the mystery personal, turning a billion solar mass enigma into a sequence of notes that resonate somewhere deep within us. That sound, the translated pulse of a distant giant, brings our journey full circle. We began with a single, startling rhythm from a small black hole in our own galaxy, a 40-minute heartbeat that defied our silent, monstrous image of these objects. From that first metronomic tick in a microquasar, we followed the trail to the supermassive breathers, the true cosmic hearts pulsing in the cores of distant galaxies. We have seen how these rhythms are not flaws in the chaos, but a natural language of the accretion engine itself, a dynamic interplay of gravity, magnetism, and turbulent plasma. They transform black holes from passive pits into dynamic, breathing entities. These steady pulses have become our most precise tools, acting as sonar to map the warped space just outside the event horizon, and as potential speedometers to measure a black hole's hidden spin. They remain captivating mysteries, their very persistence challenging our best models of how order can arise from such profound violence. Each new observation, from the fading of an old rhythm to the flickering birth of a new one in a star's destruction, brings us closer to understanding this cosmic cadence. The universe is not a static painting, it is a living, breathing symphony, and black hole breathers are one of its deepest, most resonant rhythms. So the next time you look up at the dark sky, remember this. In that immense silence across unthinkable distances, colossal hearts are beating. Their steady pulse is a reminder that even in the darkest places, the cosmos moves with a rhythm we are only beginning to hear, and every new beat we discover is another note in our growing song of understanding.